Hi, generating function give a very nice way of dealing with the case when we have a random number of variables to be summed up, and I would like to explore this here a little bit in this video. Our setup will be that we have x1, x2, and so on, the non-negative integer random variables. RV stands for random variable as usual, and we have y, again non-negative integer random variable. Moreover, these are completely independent, so the x's are IID, so they are independent of each other, but the joint distribution of the x's, the joint independent distribution of x's, is still independent of the y, so all this set of random variables are fully independent. That's the starting setup, and I'm going to define z to be the sum from 1 to y of the xi's, or if we want, we can say x1 plus x2 plus and so on up to xy. And just a convention here that this is actually equal to 0, so the definition is that this is equal to 0 if y is 0. So empty sums, when y is 0, then the sum is empty. Empty sums are considered to be 0. Okay, of course it can also be 0 if you have a bunch of x's and all of these x's happen to be 0. Okay, so it's a random number of these IID x's summed up, a random integer, non-negative integer number of them summed up. What I want to know is the generating function of this thing. What is the generating function p of z? Okay, so I want to know the generating function of z, and by definition this is the expectation of exponent of s to the z. Expectation of s to the z. If I don't put any parentheses, that means that expectation of s to the z, where s is supposed to be a number between, say, 0 or 1. And so the definition is that this is the expectation of s to the sum from 1 to y of the xi's, because that's what z was. Okay, and now here is a thing first. It is actually the same as the product of the s to the xi's from 1 to y. Okay, is the product of the s to the xi's from 1 to y, and at this point it would be tempting to say that the xi's are independent, and so we should make some kind of a product of the expectation. It's very tempting to say, but it's actually just as is. It is wrong to say that this would be the product of the expectations. This is wrong. Okay, this is not the case. This is all wrong. Why is it wrong? Well, if you look carefully, here there is an expectation of a complicated expression of random variables. So this object here is a non-random number. This expectation is a non-random number. It's just some fixed non-random number, whereas this one is a function of y. It's a random number here. Clearly these two cannot be equal. Okay, so be careful. We don't have a right to bring this random y across the expectation. We cannot do that. But there is something we can do, and that's a tower rule. So let's use a tower rule. Let's use a tower rule by conditioning with respect to y. Whenever you see a random sum or random product, then it's always a good idea to condition on the number of variables we have. So I'm going to take an expectation of this whole thing conditioned on y. At this moment, this inner expectation is a function of y, and if I take an outer expectation with respect to that function of y, with respect to actually the distribution of y here, then I'm gonna get back the unconditional expectation, the original total expectation. So what's the point in doing that? Well, hopefully everybody remembers that if y is given, then y is not random. We can actually pull out or take out what's not random. given y is not random. So for this conditional expectation, y behaves like a fixed non-random number. So for the conditional expectation, I do have the right to swap the expectation and this product here. Okay? Given y, the xi's are still IID because of this total independence property. Given y, the xi's are still IID. Given y behaves like a fixed non-random number. So keeping the outer expectation as is, I do have the right to swap the product and the conditional expectation of Sxi given y, and that's again because even if I condition on y, still the xi's are independent among each other. Moreover, if I condition on y, that doesn't change anything about the distribution of xi, again because of this full independence property. If I condition on y, the expectation of s to the xi stays the same, so I don't actually need the condition inside these expectations. So I have the expectation of the product from 1 through y of the expectation of s to the xi without any further conditioning. Like this. Okay? So that's again, this step is because the y and the xi are independent. Okay? And inside here, I recognize the generating function of the xi's, which is all the same. So I'm just going to say x1, it doesn't matter which one I take. The xi's all have the same distribution, so I could just take the generating function of any of them, say the first of them. And so what I have underneath the big expectation with respect to y is just a y time product, a y's power of p of x1s. So p of x1s is raised to the y power, and I have an expectation of this whole thing. If I don't have any further parentheses, that means that y is inside my expectation. So I could actually write this out if you want, but I most often will not. Okay? And finally, notice that p of x1 of s is a generating function. It's easy to check that for s between 0 and 1, this is a number between 0 and 1. I can raise this number, I can raise this object here, this orange object, raised to the y power and taken an expectation with respect to y. What is that? Well, that's the generating function of y itself at the orange object, at whatever I saw inside here. And what is the thing I saw inside there? Well, that is the generating function of x1 or any of the x's at s. So what I conclude is that the generating function of this random sum is py of px of s. It's a composition of the generating functions for y and x. Okay, so that's the main point of this kind of little video, that take the composition of generating functions and that will give you the generating function of a random sum like this, for at least for non-negative integer variables. I would like to show you an example, a quick and easy example, and we'll see more interesting examples later on. My quick and easy example is the following example. So let's take y to be a Poisson random variable. And for example, we can imagine that we're looking at a post office, and this could be, say, the number of people who enter this post office from 9 a.m. to 10 a.m. Poisson is actually a very good distribution for that. It's a very good model of number of people entering the post office. And then let's assume that xi is going to be IID Bernoulli of some parameter p, and moreover these two are independent. And if I want to continue the story, Bernoulli means that it's 0 or 1, right? 0 or 1, that's what Bernoulli is. 0 with probability 1 minus p and 1 with probability p. And suppose that this is the number of people, and suppose that what I want to do is I'm going to take this as the indicator that the ith person in the post office is a female. So it's going to be, so xi is going to be the indicator that the ith person to enter the post office so suppose we're talking about people in the post office, the ith person ith person to enter the post office is a female. Okay, that's my Bernoulli, and I'm assuming that people entering the post office is independent of each other, and it's also independent of the total number of people, whether the person is a male or a female. And so if I do this sum from 1 through y of xi, then I'm counting zeros for males and ones for females, so this will give me the total number of females entering this post office. And I want to find out what is the distribution of this number. Okay, it's clearly a non-negative integer. And one way to find out, maybe one of the best ways to find out, is to first of all call it z, is to just apply what we had in the previous page. So p of y of p of x, so composition, I'm not sure if you actually saw that, p of y of p of x, a composition of the generating function. So composition of generating function for y and the generating function of the xi, say x1. So let's see what these are. Well, we have covered both the Poisson and the binomial random variable. The Bernoulli is a special case of binomial, so we can apply that, or we're gonna do this in a second. But let's do the Poisson first. So this is gonna be e to the exponential of lambda s minus 1 for Poisson, and for Bernoulli, you can either just plug in the binomial thing for n equals to 1, or you can just quickly find out yourself. Expectation of s to the x1 is going to be s with probability p and 1 with probability q. So this is ps plus q. And so I can plug in these these functions here. So exponential of lambda times something minus 1, but what is that something? Well, instead of s, I need to take whatever I see inside my generating function. So I need to take this box here, which is the generating function of x1, in other words ps plus q. So I have to put here ps plus q. Okay, let me write it out again without the orange thing. ps plus q minus 1. Now q is of course 1 minus p, as always so far. So q is 1 minus p, and 1 minus q is p, and q minus 1 is negative p. So in fact, what I have here is exponential of lambda ps minus p, or exponential of lambda p times s minus 1. And if we carefully look at the generating function for Poisson, which y was Poisson lambda, then we recognize that this is actually of the same form, except for one difference: lambda became lambda p. So what we conclude from here is that we end up with the generating function of a Poisson random variable with parameter lambda p at s, and from here we conclude that z actually must have this distribution Poisson of parameter lambda p, because the generating function uniquely defines the distribution. So if you look at the number of females only, and each person is a female independent of everything with probability p, because this is Bernoulli p, then you end up with the fact that the number of people entering the number of females entering the post office is Poisson with parameter lambda times p. If you ever came across Poisson processes, then you're not very surprised about this, because if you recall what thinning of a Poisson process, or if you want a Poisson random variable does, that's exactly what's happening here. If you drop every count with some probability and keep every count with some other probability independently, then the ones you kept is Poisson again, except the expectation of course changes from lambda to lambda p. In fact, the ones you dropped is of course also Poisson, so if you want to count the number of males, that's going to be again Poisson lambda 1 minus p. And one thing we don't see from this argument is that these two will actually become independent. But that's a story for a different video perhaps.